Have you ever stopped to think about the invisible rules that run our world? I'm talking about the pushes and pulls that decide, well, pretty much everything, from how we walk down the street to how a massive skyscraper stays standing. Today, we're diving into the amazing physics of force and pressure, and we're going to figure out how a tiny little pin can actually be mightier than an elephant's foot. So let's kick things off with a puzzle, one that kind of messes with your head. You've got an elephant, right? It weighs thousands of kilograms. And then you've got a pin. It's practically weightless. And yet that tiny pin can create way more pressure than an elephant standing on one foot. How on earth is that possible? Well, we're about to find out. To crack this mystery wide open, we first need to get a handle on the main character in our story, force. It really is the fundamental concept behind every single interaction, every bit of movement, and even every moment of complete stillness. So, what is a force? At its heart, it's just a push or a pull. That's it. Now, we can't see the force itself, but we can definitely see and feel its effects all around us. Every time you kick a ball, or lift a grocery bag, or even just sit in your chair. And we measure it in newtons, which is a little nod to the genius who figured all this out, Sir Isaac Newton. Now, this brings us to something that trips people up all the time, the difference between mass and weight. Your mass is basically the amount of stuff you're made of, and that number stays the same whether you're here on Earth or floating on the moon. Your weight, on the other hand, is a force. It's the pull of gravity on your mass, and that's why it's measured in newtons. Okay, so we've got force down, but, just knowing what a force isn't the whole story. The real magic, the fun stuff, happens when we learn how to play with it, how to actually multiply its effect, and that is the science of leverage. The secret ingredient here is something called the moment of force. It sounds a little complicated, doesn't it? But it's not. It's basically just turning power. Think about opening a really heavy door. If you push right next to the hinges, the pivot point, you got to push really hard. But if you push on the handle, way on the other side, it swings open easily. You're not pushing harder, you're just creating a bigger moment. And we use these moments all the time in everyday tools, which are usually organized into 3 classes of levers. You've got your first-class levers, like a pair of scissors, where the pivot is right in the middle. Then there are second-class levers, like a wheelbarrow, where the load is in the middle. And finally, third-class levers, like a fishing rod, where you put the effort right in the middle. Each one is just a clever way to make a job easier. And believe it or not, it all comes down to this super simple formula. The turning effect, that's the moment, is just the force you apply multiplied by the distance you are from the pivot point. The longer that distance, the more turning power you get for the exact same amount of effort. It's why a mechanic uses a long wrench to get a stubborn bolt loose. They're maximizing that distance to create a huge moment. All right, we've covered force and we've covered leverage. We now have all the pieces of the puzzle we need to go back to our big question and finally figure out how a tiny pin can outmuscle a giant elephant. The final clue is all about pressure. See, pressure isn't just about how hard you push. It's about how focused that push is. It's the amount of force you apply over a very specific area. A gentle tap with your finger is one thing, but that exact same tap with the tip of a needle? Totally different story. And here it is. The whole secret is right in this formula. Pressure equals force divided by area. Now look close. See where area is? It's on the bottom of the fraction. That is absolutely crucial. It means for the very same amount of force, if you make the surface area smaller and smaller, the pressure gets bigger and bigger. And boom, here's our answer. An elephant puts down a huge force, its entire weight, but that force is spread out across 4 big feet. So you have a high force over a high area, which equals, surprisingly, low pressure. That's why it doesn't just sink into the ground. Now the pin, you apply a pretty small force, sure, but it's all concentrated on a point so small you can barely see it. A small force over a tiny, tiny area creates an incredibly high pressure. And just like that, mystery solved. But hold on, we're not done yet. Because this isn't just a story about solid objects bumping into each other. These exact same principles of force and pressure are at work all the time in the fluids that surround us, in the water we drink, and the very air we breathe. It's a pretty wild thought, but right now, all of us are living at the bottom of a giant ocean of air, and the weight of all that air is constantly pushing down on everything, including you. We call it atmospheric pressure. The only reason you don't feel like you're being crushed is because it's pushing on you equally from every single direction. So how do we actually use this invisible force?
Well, let's look at something as simple as a plunger. When you push it down, you're forcing all the air out from under that rubber cup. That creates a little zone of low pressure. Then, the higher atmospheric pressure on the outside pushes down and does all the hard work of clearing the drain for you. You're not really doing the work, you're just setting the stage for a pressure battle.
And you guessed it, the exact same rule works for liquids. The deeper you go, the more water there is piled on top of you, and the greater the pressure gets. Anyone who's ever dived to the bottom of a deep swimming pool knows exactly what this feels like in your ears. And that simple idea has some massive, real-world consequences. I mean, engineers have to deal with the absolutely immense pressure that builds up at the bottom of a reservoir. That's why dams are these incredible feats of engineering, built with unbelievably thick bases just to hold back the crushing force of all that water. So when you really step back and look from these giant structures all the way down to the smallest household tools, you realize we are constantly, and usually without even thinking about it, using these fundamental rules of force and pressure. They are the hidden architecture of pretty much everything we build and do. I mean, seriously, once you start looking for them, you see them everywhere. When you use a drinking straw, you're just lowering the pressure inside so the atmosphere can push your drink up. Syringes do the same thing. Submarines need reinforced hulls to survive deep-sea pressure, while giant cargo ships float because of buoyant force. Even the simple act of walking only works because of frictional force. So the next time you see a huge ship floating, or you use a pair of pliers, or you even just take a breath, you're witnessing these fundamental invisible rules in action. The principles themselves are pretty simple, but what you can do with them is endless. The real question is, now that you have this new way of seeing, what other parts of your world will you start to understand?